we will start a new chapter, estimation for kinematic models. These are the contents, discrete time kinematic models. We have um, already studied some dynamic equation, which is also called the state equation and the kinematic models, and we already used these models in the Kalman filter, and then explicit filters for noiseless kinematic model, then prediction and smoothing. So kinematic model or the motion model, and they are mathematical model that describe the motion of object without consideration of forces, and it is very well known that they are defined by setting a certain derivative of the position to 0, and in the absence of any random input they yield motion characterized by a polynomial in time. So for example, uh, this is we have already studied that f of k into x of k. Okay, this is the some transition matrix, and this is the state, okay, at time k, and this will give you the kinematic model or the motion model for the x of k plus 1. So we have already used this model. uh, so here uh, there is no additional variable like v of k, the noise variable. So in the absence of any random input like v of k is not available, they yield motion characterized by a polynomial in time. Means they yield the motion by using this formula f of k and x of k. Not realistic to assume that there are no disturbance. One can model them as a random input. So we add some random noise like this. We add some random noise v of k in the kinematic model. So in general, the state observation are done in discrete time. The corresponding discrete time state equation are needed. So there are two models: white noise acceleration state model, which is two-dimensional per coordinate, and VENA process acceleration model, uh, which is three-dimensional per coordinates. So white noise acceleration state model is a second-order model, and sometimes it also known as a constant velocity model. Okay, so and the VENA process acceleration state model is a third-order model. So sometimes it's also known as constant acceleration model. Okay, so because in case of second order model, the uh, f of k is a 4 by 4 matrix, and x of k is a 4 by 1 vector. Means it include only the two-dimensional position and two-dimensional velocity. So this is the second order kinematic model. So here if we add the if we add the v of k here, then this whole equation is called the white noise acceleration state model. And so as this state transition matrix, when multiplied with this state x of k, then it add the velocity to the state. So that's why it's called the constant velocity model. So in here in this case, there is only information of velocity available. Okay, so and on the other hand, when a process acceleration state model is a third order model, and sometimes known as constant acceleration model. So in this case, f of k is 9 by 9 vector, and similarly x of k is 6 by 1. So in this case, x of k include the two-dimensional position, two-dimensional velocity, and two-dimensional acceleration. And when f of k, which is 9 by 9 matrix, is multiplied with the x of k, then this will add the acceleration. And it is called the sometimes it is known as constant acceleration model, because when to get the next state of the object, like k plus x of k plus 1, we used this constant acceleration model, which which add the acceleration to the previous to the current state to get the new state, like x of k plus 1. So if we add the white noise acceleration, like v of k, this is called the process noise or white noise acceleration model. So this whole equation is a when a process acceleration state model. Okay, so when a process acceleration model state that adding the white noise in the kinematic model to get the noisy object state for the next time state, like x of k plus 1. So in many applications the same model is used for each coordinate. And some application, for instance in air traffic control, one can use the two third order models for the horizontal motion, and the second order model for the vertical motion. So the kinematic model in discrete time is defined as follows. Okay, for example, as we have already discussed, that taking an expected value of the process noise, giving you a standard deviation. This is a standard deviation, and this is the impulse. This is the impulse. Okay. Uh, so when in terms of the program code, we can write here like impulse, like identity matrix, like identity matrix. So this the and the expected value of the process noise has a zero mean and the white sequence. Okay, so which enters into dynamic equation is follows, like this one, v of k, and this is the kinematic model, and we add the some process noise. Process noise is entering into the dynamic, or we can say kinematic model, and this gamma, this gamma sign is the noise gain, which is an x-dimensional vector. For example, if your x of x is 4 by 1 vector, then the gamma is also the 4 by 1 vector, which is multiplied with the process noise. Now the assumption in the second order model is that the object undergoes a constant white noise acceleration v of k, the process noise, during each sampling period of length t. Okay, so your v of t equals to v of k, where t belongs to k times t, where t is the sampling period between each scan. For example, if t equals to 1, then the k scan have a sampling difference of 1 second in each time scan, and the t belongs to the interval of the kt and k plus 1 into t. Okay, and that these oscillations are uncorrelated from period to period. So it's like a piecewise constant oscillation model. For example, this is here is a k, and here is a k plus 1. Then the piecewise constant model, like here, like this one. So it's piecewise, like at scan k, this is uh, the constant oscillation, and at k plus 1 it goes down here. And so this type of signal is called the piecewise signal. And each each piece are uncorrelated from period to period, like from it is not correlated from period k to period k plus 1. So the white noise has a is a piecewise constant oscillation. If V of k is constant white noise oscillation during the kth sampling period of length t, the increment in the velocity during this period is V of k. Okay, so while the effect of this acceleration on the position is V of k t square divided by 2. Okay, so here we are trying to define uh, the gamma here, like this one. So which is said that the gain, which is multiplied with the v of k, is like that the v of k is the constant velocity, constant white noise acceleration during the kth sampling period. The increment in the velocity during this period is v of kt, while the uh, this t, and while the effect of this acceleration on the position is t square over 2. Then the state equation for the piecewise constant white acceleration model, or sometimes we call it as a discrete white noise acceleration, DWNA model, which is a second order model, is then becomes like this: f of f x of k, gamma, and v of k. So where v of k is the process noise zero mean white acceleration sequence, and the matrix f is like this. We have already known that it is the matrix is the 4 by 4. This is actually 4 by 4, and the this is the identity matrix, like suppose I 2 by 2, and this is also the 0 2 by 2. Okay, and also this is also the uh, t into identity matrix. Okay, so this is the 4 by 4 matrix, and which is we say that is the second order model. This is second order, and this gamma, uh, this is also the 4 by uh, 2, the 4 by 2 vector. Also this is the t square is multiplied with the identity matrix. So so that uh, the gamma is the noise gain, okay, which is multiplied with the v of k. Now the covariance of the process noise multiplied by the gain gamma of k is given by, so the covariance taking the expected value of the process noise and the noise gain is equals to the covariance. So here we, if we put the value of the gamma here and here, so here we can see that this is the v of k and the transpose here. So if we put the value here like 2 1 upon 2 t square and t, okay, and this is same by the standard deviation, and this is the taking transpose like 1 upon 2 t square and t. Okay, so this will give you this equation when we multiply this thing to this thing. So this will give you this equation. So this is the your covariance q, and this is the standard deviation where this equals to gamma square. So this is a q. So the physical dimension of v and sigma v is the length per time square, that is of acceleration. So how we choose this value, the standard deviation for the process noise variance. This is a guideline for the choice of the process noise variance. For this model, sigma v should be of the order of the maximum acceleration magnitude. So this acceleration is not for the object state. This is acceleration of the white samples. Okay, white noise sample. The acceleration, this acceleration indicates the acceleration of the white noise samples. Okay, this is white noise samples between each sampling period, between each period t. Okay, so this is acceleration of the white noise samples between each period, and this should be order of the maximum acceleration magnitude am. Practical range is for 0.5 am and to maximum am. So here we choose the q like this one, 0.5 to maximum of am. So a nearly constant velocity model is obtained by choice of a small intensity of the q in the following signs, like the changes in the velocity over the sampling interval, which are order of the sigma sigma into t, have to be small compared to the actual velocity. Okay, so the order of this white the acceleration have to be small compared to the actual velocity of the object state. So another type is the VENA process acceleration model, which is a three-dimensional, like three-dimensional state vector or three-dimensional kinematic model, and this is the same as the previous equation. Just the dimension is now 3. So here x of k is 9 by 6 by 1 vector, and f is 9 by 9 matrix, and gamma is also the 9 by 3 vector. So here this is uh, noise gain, which is multiplied with the process noise. So in this model, the uh, white process noise v of k is acceleration increment during kth sampling period, and it is assumed to be a zero mean white sequence that is acceleration is a discrete time Venner process. So when we put this value in here covariance, uh, gamma into sigma standard deviation into the gamma complement, then you will easily get this matrix. So again, the choice of the standard deviation is same like in the second order model, uh, like this: zero point 0.5 maximum, a maximum, less than a maximum. Okay, now first use the filters for noiseless kinematic model. For example, least square estimation for noiseless kinematic model. Consider an object moving with a constant velocity without process noise. Okay, noiseless means there is here we are not adding the process noise. We have k. So uh, the estimate of the initial position and the recursive form, the constant velocity is obtained using the noiseless kinematic model, such as this is the noiseless kinematic model, because here this is t. Okay, okay, so here we are not adding the v of k. So the system is the noiseless kinematic model. And so in the recursive form, the estimator propagating the state using the kinematic equation like above is like this one. This is the uh, recursive propagation um, determined by the estimator. Assuming a uniform sampling rate with sampling period t, we obtain like this one. This is estimated value at time k plus 1, condition on at time k plus 1. So this is the same as this one. And how we get, as you already know, if we add the k plus 1 times t, then it will add the velocity and the initial state, or you can say the initial uh, state estimate at 0 time. This is same, this thing is same like x of 0, condition is 0. Okay, so this is estimate of initial state. So x of 0, condition of 0, or x of 0 k plus 1 is um, already given to you. Okay, is already given to you at the first time. Initial state is already known, and then estimate of the this state is obtained by 2-point differencing, like this one. If we uh, uh, update this thing with using the 2-point differencing, we will get the estimate of the 0 k plus 1. So this is the estimate of initial state. And therefore what will be the next value in the next scan, like k plus 1 and k plus 1, the estimate of the next scan. If we add this f of k, uh, the k plus 1 times t, then it will give you the next scan estimate. How about the gamma filter for noisy kinematic model? So this is the same. uh, so the prediction equation, this is the gamma filter recursion for the estimate of the current state is this one. This is the gamma filter output. This gamma filter output equation. So, and this is the prediction, the previous scan, and this is the gain, and this is the residue, like v. Okay, this is the residue. So here where this prediction is obtained by the f into the estimate of the f into estimate of this one. And similarly, the mean value of the z is obtained by the h. This is a measurement and the prediction of the this thing. Okay, this is the same thing. This is a state equation, and this is the state observation. This is a state observation. So, and the state observation is obtained by using the h, which is this is also uh, 2 by 4 vector, 2 by 4 vector, like the one is the identity matrix and 0 is a zeros matrix. So this is 2 by 4 vector is multiplied with uh, initial predicted state. This is predicted state like this one, and it will give you a state observation of the previous scan. And the associated covariance with the estimate is from, as you know, the previous lecture, like this one. Again, it is 1 minus the Kalman gain into h k plus 1 into the previous the predicted covariance. Okay, this covariance belongs associated to this state. Okay, this covariance is associated to this covariance, and this is covariance associated to this covariance. So this is the output for Kalman filter, the state estimate and the state covariance. And here also, what is a p? The state prediction, the state the state prediction covariance is obtained by using the this is f and into the initial covariance, initial covariance, and this is f transpose. Okay, so similar results can be obtained for the discrete wide process acceleration three-dimensional model. In this case, the f will be in the DWPA, f will be 9 by 9 matrix, and for the three-dimensional means the three-dimensional position, three-dimensional velocity, and three-dimensional acceleration of the auxiliary state. So due to the absence of the Poisson noise, the state covariance converges to zero, and so does the filter gain. So prediction is the estimation of the state at time j beyond the data interval, that is based on the data up to an earlier time k less than j. Okay, here data means the measurement z. Okay, so as you know, the z k is like z of I. Okay, where I equals to 1 to up to k. So this is the I belongs to 1 to 3, k is k. So z set is the z1 means measurement at scale number 1, measurement at scale number 2, so z1, z2, and so on. So the prediction of this estimate, if we write here j, because here the j indicated, so the prediction is the estimation of the state at time j beyond the data interval based on the data up to an earlier time. So here k is less than j. So how to give the notation on the prediction? So the prediction is j. What is the predicted value of the jth scan condition of k means you already know the k value. Now you are predicting for the jet scan is equals to the expected value of the x of j conditioning on the zk. So it means to find the predicted value of the x of j, the z of k is already known. Okay, means the data up to the time k is known to you. So there are three types of prediction: fixed point, fixed lead, and fixed interval prediction. Fixed point is this is done to be fixed point in time j equals to n. Okay, that is intercept time based on the data. When we talk about the data means some measurement like this one. Okay, so this is done to the fixed point in time j equals to n based on the data up to time k, where k is changing. Okay, where k is changing because in each iteration the number of scan is changed, like 1 2 3 4. So to find the prediction at any fixed point like j equals to uh, 5, like j equals to 5, then your data must be available up to the 5. Okay, your data must be available up to the 5 to find the prediction at the 5. Okay, and fixed lead prediction is this is done by for a fixed number of l steps ahead. Means the ahead means lead, which lead the k. So here for example L is the lead, then L is leading the k. So J will be equals to the this is the fixed lead scan. Fixed lead scan is equals to the k plus L, where k is varies and L is a lead. Okay, so if k is 5, if k is 5, then if lead size is 3, means at each scan the lead 3 is you can say is accumulated in this scan. Like if k is 5, then the j equals to k, 5 plus 3 is 8, like this one. So here the lead equals, which is equals to 3, is leading the kth scan at j. So here you are finding the prediction at leading point, given that you have already known the measurement up to 5 scan. And in this fixed interval prediction, this is done based on the measurement data from the fixed interval up to k time n. Here k equals to n means the measurement up to n scan is already known to you, like this one. Okay, for example, you can see in this figure the fixed point for the fixed point is n equals to 8, and it means this is the fixed prediction. Okay, this is fixed prediction. Now to get here you are predicting each scan by uh, individually, like this. Okay, equals 3, and then it will predict the next 4 and then 5, like this one. So 3 to 3 is 4, and 4 to 5, then 6, and then this equation, this fixed point prediction, like this one. So if j equals to 8, okay, then the measurement up to time k, which is actually changing, like 1 2 3 4 5, okay, is all available. And the fixed lead, for example, this thing, for example, if you are k equals 3, if you are here 3, okay. Then and L lead is 3, okay. Then what will be the J will be the 3 plus 3, okay. K is equal to 3, this is K, and this is the lead. Then using the three position, three scan prediction, you will get the number sixth scan. J equals to 6 scan prediction, okay. So in this case, your estimated value of the J 6 condition on the K plus L, okay, this equals to the expected value of x of J, which is your 6, and condition around ZK, okay. ZK means which is actually 3, means based on the measurement which is available to you up to scan number 3, you are predicting the state at uh, which is leading to here. Okay, so and what is the fixed interval n? So suppose the fixed interval length is n is equal to 5. Now what will be the J? J will be the K plus N, okay. In this case, J equals to K plus L. In this case, the J equals to the K plus N. So for example, the length interval is 5, okay. And here, after predicting, after the available measurement up to 5 scan, we are uh, we are getting the prediction of the next scan, means number 6 one. And then after in the when j equals 7, after the measurement available, or the all prediction at up to 5, the next scan prediction can be calculated like 7, okay. And at the same time, during the same interval length like 5 scan, we can calculate the uh, prediction of the state for the scan number 8.
So that's
So
the end
these
of the
are the three
lecture.
types
Thank you
of
for watching my video.
the
Please
prediction.
subscribe my channel